Okay. Good afternoon, everyone. Thank you for joining our seminar series. So this series is mainly about financial mathematics or the cutting edge technologies in finance. So today we are very happy to have Professor Songping Zhu to give us a talk about a new integral equation formulation for American put options. So before he deliver his talk, let me introduce you briefly about our speaker. Professor Songping Zhu is a senior professor of applied mathematics at the University of Wollongong, Australia. He graduated from the University of Michigan with a PhD degree in 1987. He has already published over 200 papers in international journals such as Mathematical Finance and Conference Proceedings, and attract over $2 million of funding support from ARC and private industries. His research has been recognized both nationally and internationally. So without further delay, let's welcome our speaker, Professor Zhu, and thank you very much. Thank you, Professor Zhu.
Okay. Thank you, Patrick, for the nice introduction as well as the kind invitation. As I sort of briefly commented, it's the COVID has changed the whole world. In particular, the research atmosphere around the whole globe, and it was very impressive to see younger generation like Patrick's. Please notice I'm using the plural. Patrick's not just himself, right? There's lots of younger guys like Patrick and Professor Pang, who has taken over all this research enthusiasm from the older guys like myself and push forward. I was actually, there's something I know probably Patrick or Professor Pang more than what he realized. Right? Anyway, I can't disclose on those, but I really appreciate the invitation, which this sort of thing drives the further research, and then people who participate may or may not exactly do what I've done. But this sort of thing is there's also part of the reason why I chose this topic. When I give a talk, I always trying to maintain some part of entertainment rather than just technical part. So this topic, I think probably suits that point in the sense that I'm trying to tell a story, including some of my own students in terms of why research can be fun, and also why research eventually, even some of the audience, they may eventually become a professor or so, why the teaching and the research are not really totally separated. So they are somehow interconnected. I'm hoping that through this talk, this gives you an example of that point. Okay, so the title of the talk is a new integral equation formulation. It's a slightly longer than I probably ideally would choose. So it is not just the integral equation itself, it's the formulation for American option problems. Let me acknowledge that this was based on a joint paper with my former student Professor Xinjiang He, and then also Associate Professor Xiaoping Lu, who's still at the University of Wollongong. So this was a paper a few years ago, but then I just thought it's probably talking about this, to me, is more appropriate than some newer ones. And although the newer ones has other merits, but then this one, I thought I can at least achieve the purpose of not only showing how to choose a topic that could eventually lead to a good journal paper, and not also something reasonably entertaining. Now, I'm pretty sure if you look at the Patrick's own achievement or Professor Pang's achievement, he has done quite a lot already to someone, for someone of his age. For the second point, I'm not sure about this. At this stage, he wants to entertain people. He probably more focused on scientific achievements, which he has done a lot. So Here's the outline of my talk. I'm going to somehow divide this into 5 parts. I'm going to talk about the background of this problem, which probably all of you know quite a lot by now. It's a reasonably old problem, but then the equation I presented is actually new. In fact, one of my PhD students is currently working on it and trying to make it better, or trying to improve it, or trying to extend it. So we're still working on it. The reason is it has quite a few nice advantages in comparison with the traditional one. So I'm going to go with a little bit of review, but then I will highlight the main points of this particular integral equation formulation, and then of course in particular why it is so good for American options. I hope at the end of this talk you gain something, or you get some knowledge out of this, because there are lots of financial derivatives also. They all are from American contract, and hopefully my talk is not just limited to the option. This actually, it can be extended to any other American style derivatives. Right? So I'm going to follow a very simple example, and then most of the time I'm going to try to give you just rough idea rather than a lot of details. For the details, you can audience can easily read papers. That's also another point, another belief, that I never really try to talk a lot details during a seminar. I believe a seminar is mainly to show what's the idea, what's behind, and that kind of thing. Okay, so I started with it. Let me start. I cannot, for the time that Professor Pong gave me, I cannot go for too long. I do have some slides I want to spend more time. Others I'll try to fly a bit faster. This is, everybody is so used to it. This is something what we call underlying. If we're trying to derive a fair price of an option written on an underline. So what we are presenting here today, and like, I understand there are people who, especially in finance, they want to predict, let's say, a stock price or that sort of thing. That's not what we do. And then there are other nice techniques they do, but then what we like is really, when I say so far, my understanding is that there are 2 main achievements, in my opinion, in terms of financial mathematics or mathematical finance, where math is beautifully used for financial problems. One of them is called the option pricing problem, and another one is this portfolio selection problem. Those 2 large classes, right? Well, I think there are small minor ones here and there, but then at the moment, I think that the most elegant achievements would be in those. So here I'm going to fly quickly on this. I'm sure that everybody knew about it. What's an option? This is basically a contract that the holder, one side of the holder has a right, but no obligation, whereas the other side has just obligations. And then one of the controversial problems, at least since the beginning of the 20th century, was to price it, how much it's worth. And then a big problem is that this sort of contract, they will be exercised at a future time, for which we don't really know much at this stage. That's the main difficulty. I mean, some of my students, I don't know even by the time they graduate whether or not they actually have appreciated that simple fact. That's the fundamental difference between this sort of contract with other conventional contracts. And then there's a so-called European option or European style. That's basically for that right you can exercise at the end of the period, or the contract period, which is a future time. And again, for American options, then it's between now and the future time that you have an additional right that you may exercise for the holder. You may exercise your right at any time prior to the expiry time of the contract. Now, because of that additional right, then mathematically, this is where I actually started my research in this area. It's so beautiful that it casts the problem mathematically into what we call the moving boundary problem, which is highly nonlinear. From no matter which angle or point of view, you could go from the martingale point of view, or you can go from the the PDE point of view, which I'm more familiar with, then the problem mathematically becomes a nonlinear problem. It is that nonlinearity that has attracted many people like myself into the area. It is the difficulty of that nonlinearity that has made the problem non-trivial. Otherwise, from mathematical point of view, apart from the great contribution of this Black and Shoals, who sort of settled down the debate between people about how an option price should be decided on, to mainly talk about the European option. But even for that well-known Black-Scholes formula right in front of you, your teacher might be sure that this is your class ABC when you got into the new area, this so-called Black-Scholes formula for European option, or virtually for any European style contract, derivative contract. More or less you can modify this a little bit and get your so-called closed form solution. Right? So that itself, apart from what I just mentioned about nonlinearity, that was a huge contribution. I don't know if you know about the recent development about all this negative futures price, but then one of those, the development was the Bachelier was the one initially had something similar, but not exactly close. The only difference is that for the Bacheliers, it's not the log normal. So Black-Scholes took the log normal and it got to this beautiful formula. Okay, and then associated with that is the so-called Black-Scholes equation, which is a PDE. Right? That's the one mathematically we have to satisfy in order to fairly price an option contract. Now, that one on this slide, all I'm saying is a fundamental knowledge. Let me see, watch my time. Okay, it's okay. This is just from the martingale point of view. Right? You can see that you can view American style option as a contingent claim that becomes an optimal stopping problem. Now, the only thing is that here you have two problems or two mathematical formula. One is that you're going to take a supreme of expectation for future time down discounted to today, and then also you have the so-called optimal stopping time, which is the one I mentioned earlier from PDE point of view. This is the main reason that we got this so-called moving boundary. It is because this T star, which is the infimum of a function there. Okay, now that one, you can theoretically, it's very clear, except practically, if you're trying to calculate the actual price just from that alone, you may have to do the simulations or so. Right? But then very luckily, there's a great bridge called the Ito's lemma that would get us to the other side of the bridge, which is the PDE side, right? So we can cast the problem into a PDE, and then I'll do a bit of review on this. So some pioneer on this free boundary problem. That's when we talk about a free boundary, primarily that's a term used by the PDE community, which I belong to. And then Samuelson, Martin, those are the big names even before the Black-Scholes. They pointed out this moving boundary without knowing, without having the right PDE to solve. They had a different one, 65. So, and then, sorry, talking about that, and then in terms of, I'm going to briefly mention, in terms of option pricing, it depends on how you classify them. You can classify them by the models. Some of them, this is according to what we call the risk factors, how many risk factors you have. Right? If you only have the underlying, that's one risky factor, and that's one factor models, and then you have more than one, let's say stochastic volatility or regime switching, so on and so forth. That's what those are called the multi-factor models. Let me draw attention to some junior audience that there is a bit controversial in literature in terms of the counting of one factor or more than one factor models. There are different views, but then by my view, I think the right way is to depend on how many risky factors. Otherwise, there's a bit of confusion there. Okay, so I'm not going to get into too much details. So now, in terms of PDE, let me just show you that at the moment, yeah, you can replace PDE when you have a different model, a model that drives, what we call the dynamics, matches the dynamic, or match or modeling the dynamics of the underlying of an option, which is, let's say, a stock or anything else. It doesn't have to be stock or anything else that your option is writing on. So for the simplest one is this one is the winner process, right? Built on which you would have this the Black-Scholes PDE, and then the let me try to get a pen. Good. Whoops. Why am I? How am I going to get back? So hold on. Oops. I'm sorry. I'm always not very good with this. Hold on. Let me. Okay, here we go. I was trying to get a pen. Yeah. Okay. So at the moment, I just wanted to show you that there are two. This is what we call the free boundary. This is an unknown, which is the same, has the same role as V, which is also unknown from the PDE point of view. Same thing in the previous slide. If you try to do it from the in my office, I gotta keep moving, otherwise this light would shut down. All right. So the rest is for the PDE. These are called the moving boundary conditions, the two of them, right? Which makes the problem nonlinear from PDE point of view. Otherwise, if you have a fixed domain, it'll be the equation itself is linear, but then with a fixed domain, the whole thing becomes linear. And this is the other one. This one is a payoff, and then this is just for put option at infinity. When underlying is very large, this is called out of money. Okay, so now the trouble is that I have to stop this pen before I can move. Okay, let me get the pen back and then get rid of those. This is one of the reasons I hate. Hold on, where do I get the annotate? Yeah, I need to clear it. All the joins. Okay, so on this slide, I wrote a little bit. Basically, this I already said that the key issues, why the acknowledge that pricing American options is much harder or intriguing problem because of this the moving boundary, and there's a couple of other things. So this slide I already talked about. So I don't like to read slides. The next point is that I want to mention the main for American options. Primarily, there are two main sources of difficulties. One is the most dominant one is, of course, this moving boundary or the nonlinearity associated with the moving boundary, and the other one, which is less known for non PDE community, is this singularities associated with the problem at expiry time. But when you do the Monte Carlo simulation, this is less of a problem. People hardly notice it because that Monte Carlo simulation quite often smoothed it out without being noticed. On the other hand, for the PDEs, it's great. You can do it much faster, at least for lower dimensional problems. For higher dimensional problems, Monte Carlo simulations would still far more superior. But then for PDE, one of the problems associated is the singularities associated with this so-called optimal exercise boundary or optimal exercise price. Now, there were some pioneers, Casca and Kelly, 1998, Bales, the et al. Here, the Bales, Casca, and Kelly. So they published a paper in the Mathematical Finance demonstrating the order of singularity. Now it's well known, but last century, the end of the last century, 1998 or 2000, that was well done because not many people could. We knew there were singularities, but they were the first who identified the order of singularities. Okay, here on this slide, I have a diagram which I always like to use to illustrate the boundary. So you don't know this picture. Somebody told me you can view it differently. You're going to have to try to adjust your eyesight so that this point is inside towards inside. So this the black line Okay, sorry. The vertical line, vertical axis is the option price. The horizontal going this way is, can you guys see my mouse? Yeah, okay. So I don't have to keep switching to the pen. So this is the time, and then the capital T here is the future time I mentioned earlier. This is underlying price S. Now you can see this the red is the projection of the black, which is the boundary to be the free boundary to be determined as part of the problem, and the red is its projection onto the ST plane. So what we really need is this three-dimensional curve. Okay, so that's enough. Now then, quickly, I want to quickly go through some very simple review. This is also another belief of mine for seminar. I want to show a little bit of systematic way. So in terms of if we classify the problem according to approaches, we can have so-called numerical solutions, and then also another classical class would be called analytical approximation. And also, I want to very briefly mention in my own work of analytical exact solutions. Okay. Out of those three, the numerical solutions, the main disadvantage for that is that it naturally introduce errors. But then don't be discouraged by that. Even the exact solutions, they introduce numerical errors too by the time you put them into calculator or whatever. You always going to have to truncate, right? It's just there are more error sources. There are truncation errors, but then for numerical, for the analytic solution, then you don't have that source. But you may still have errors introduced by the machine errors. Right? So or storage errors or whatever. Analytic approximations methods, those has an advantage that they're fast. Especially, I want to mention in passing that today, I know younger guys, they're looking for trying to match with the trend. At the moment, one of the trends is this the so-called machine learning. Well, then suddenly this analytic approximation, maybe then it wasn't so popular, but now suddenly the analytic approximation may have its role in terms of machine learning. And then finally, I also want to mention this series solution that was done by me in 2006. That was an analytic solution, a closed form solution, except the method I use is called the homotopy analysis. And that method, the convergence of it, it wasn't available then, and it's still not available now. Then I've been thinking for 2006, by now it's about almost 20 years. Right? I've been still thinking, still working. At the moment, we can show that if we assume the convergence, then the solution converges to the right solution. But then we can, if we don't make that assumption, then we still don't have a general proof. Then pretty much after 20 years, I'm now believing that there is no such general proof, because if there was one, then the whole world would be different today, because that means we could have solved any nonlinear problems exactly. So that itself, it's a bit too much of a wish. So that's the comment I want to mentioning about that one. One of the disadvantages for that analytic solution was that I sort of solved it in the series way, in the expansion series. It's very slow. So if you want to use that in general practice, that's, in my opinion, no use at all, except if you want to compare with accuracy. On the other hand, what I'm about to show you today is extremely fast in terms of speed. So, okay. So let me very briefly, I don't really have that much time now, given that, I better go a bit fast. I don't really have, for the restrictions Patrick gave me, I'm not going to go through all these pros and cons for different methods. I'm going to focus on integral equation method, okay, because I still want to talk to you about a couple of nice stories. Integral equations, because pretty much there are many other numerical solutions. Integral equation approach is one of them, right? Some people, they view this one as semi-analytic. The reason is that semi is because by the time you cast your PDE into an integral equation, that step is purely analytic. There's no error introduced whatsoever. But then your integral equation at the end of the day still need to be solved numerically. So it's not too purely analytic. So in that sense, it is, in my view, it's still a numerical solution. The analytic part of casting into an integral equation, it's not really that much. Okay, then in that sense, we have pioneer people, Jaka and the Jamadeshi in 1992. Huang is a professor at the University of Penn State University at State College. I visited him a couple of times, and these guys, they start just like me. They did one paper and then they move on to something else. At the moment, currently he's very interested in pricing the bonds. So that's a different problem. Okay, so I myself have a couple papers in this area. I want to mention, mainly because of the time, I want to mention 3 main integral equation papers. One of them is McKim, 1965. Now this one, apart from based on the wrong equation or so, but then he was the first one who pointed out the moving boundary. And then there was a Kim, 1990 paper. Kim is the one I want to tell a story to the audience. I don't know, maybe remember I said that I want the seminar to be entertaining as well. Kim was a guy in his almost whole lifetime. He only published this one paper, one famous paper, which got cited a lot. If you don't believe me, you go to check Google, you'll see the citation number. That's really scary. Right? Even for that paper, he was a student at UPenn, not Penn State. And his father was a rich guy in Korea, and he knew that he was going to inherit a huge pot of money, and he's going to run the company by the time he finishes the PhD. So for about in US, usually it takes about 5 or 6 years to do a PhD, and then for about 5 years, he didn't do anything, no progress. And then the supervisor got a bit worried, and I'm sure Patrick supervises students now, and when they have no progress, you're worried about it. Oh my gosh. So supervisor called him to the office several times and said, hey, what the heck is going on and all that. Not particularly in that language. Right? Even then, it was a bit colorful. But anyway, so he didn't say, oh, no. It was more or less, supervisor thought that it was a playboy. Until almost the last year, he walked in with a deck of paper, handwritten, and say, hey, I found this integral equation way so that I can decompose an numerical option into 2 parts. One is its intrinsic value, European part, and its early exercise right premium. Just introduce those two. Actually, those 2 concepts were there before him, but he was the first one who quantified those 2 terms mathematically. Beautiful. Even that alone, but then it was associated with the integral equation later on, except the downside of this integral equation wasn't really, from mathematical point of view, it wasn't formulated rigorously. But then Peter Carr, by the way, I don't know if you guys knew or not, Peter Carr passed away recently, a giant guy. Right? Patrick probably met him in Sanya. He just passed away recently. His friend and Kim, I met him too in Korea. But anyway, I can't keep talking about all this. All right, so let me put it out on this slide in terms of integral equation. This is my Keynes 65 integral equation. Now, I wanted to notice that here, for the unknown function g is associated again with the moving boundary. So you're solving an integral equation here. Now you notice in this integral equation, not only do you have g, you also have the derivative of the g. What that means is that you have a higher requirement in terms of smoothness of the unknown function, which poses some problems numerically. Right? Not really huge, but then that's one of the issues. And then on the other hand, you see, look at this Kim's 1990 paper. His integral equation, it doesn't have the g prime. It only has g, the unknown function, so it doesn't require higher smoothness of the g, the unknown function. It also has certain numerical advantages. Just wanted to see difference. So ideally, the same thing for Carr's integral equation, right? So you don't see any g prime there either. Another problem, and I wouldn't say a problem, another feature is that in both of this Kim's equation, you would have eventually to carry out integrals with the two-dimensional. Even for one-dimensional problem, you have to do a double integral. So that slows down the computational speed. It is those two problems that we will solve with this new formulation of integral equations. Number one, we want to keep a known function without the derivatives. Number two, we want the integral equation is formulated in such a way that the integrals all you need is to carry out a single one-dimensional integral. So that would substantially improve the speed. Well, at the end, we end up with a byproduct. Remember, I mentioned about singularities earlier. Well, at the end of the day, we end up with a byproduct of, at least when we solve integral equation, it was singularity free. So we were very happy about it. Now, let me show you the details. Okay, so very quickly, in terms of I'm looking at my watch, we have a PDE system, the one I showed you before. The point is that we can solve it in many other ways. That one I skipped, right? You don't have to solve it in integral equations, but if we want to cast into the integral equation for this one, now this is the one that we're trying to. This is the first time. Before it was always the same PDE system. Now I'm going to try to cast, or actually change the PDE system to a different one to start. This is a different one. As you can see, the title here, I'm saying a different PDE system based on what we had before. So all you see is that eventually we are formulating a PDE in terms of theta, which is one of the Greeks. And you have the delta, all this, and then theta is one of them. Basically, theta is the option price, a partial derivative against the time. So we're going to cast it into a PDE in terms of theta. Now, very soon you'll see the advantage of it, and then very soon I'm going to also show you at one slide how we got this. This is the point why I'm in the introduction. I was saying I was trying to link the research with the teaching. So I'm going to point that out in a minute. So at the moment, without going in a lot of details, basically I'm making some variable changes and then introduce some new functions. B is related to the SF. SF is the free boundary of the unknown function to be solved or to be found, just mainly non-dimensionalized. So you got a new unknown function B there. Okay, B is still a function of tau. Tau is time to expiry, T minus capital T minus T, SF there. Okay, so then now, as I said earlier, we're trying to establish a new PDE system for this theta. Theta is the dp d tau, the partial derivative. And it is well known in the literature that on the free boundary or on the exercise boundary, that the theta equals to 0. This has been proved before, including some of my own papers back to the 90s, and people knew this. Okay, and then we can also derive another condition out of this. If you differentiate from the second boundary condition before, you get into this, which is the second boundary condition. It changes to this. Okay, so now we still, if we want a PDE system on theta, we still need an initial condition and a boundary condition. Okay. So that the initial condition, we can use the PDE. I'm not going to go through a lot of details. If you use the PDE and trying to do a bit of derivation, you'll see that it gives you this theta at tau equal to 0, gives you a direct delta function. Now, later on, I'll mention this is part of the beauty. Without this direct delta, we wouldn't have got what we already achieved. So this is sometimes is frightening, but that's mathematically this is beautiful. So this is the direct delta. You can take a little minutes. I'm not going to go through all the derivation. It's mainly from this term. All the rest of the term, once that's the direct delta, then they're less important. It's all dominated by this term, which is, by the time you think about it, it makes a lot of sense, because this is the diffusion term. In terms of a parabolic equation, we're talking about a diffusion process. On the other hand, well, sorry, we also have that boundary condition theta goes to infinity. This is straightforward. All you need is just take a partial derivative. Okay. Now, then we rewrite all this into a new system in terms of theta. So now you got a similar equation, right? Now you except you see in terms of boundary conditions, they're all similar. I haven't really changed much, except now one of the your initial condition becomes a direct delta, which is fine. Eventually, once I cast it back, I will get back everything I need. Okay, so roughly at this slide, everything is still the same. I haven't really changed a lot. Okay, now here's the key point of this whole thing. I'm going to spend a bit more time on this. First, we need to make use of this property that this B function, or the free surface, is a monotonically increasing function, for put option, is a monotonically decreasing function of tau. It's a monotonically increasing for put option of t, but a decreasing function of tau. That monotonicity needs to be exploited. In the before, people did it, but I've never seen anyone who so explicitly exploit the monotonicity until this paper. So what we do is that we now change our view angle. It's the problem nature hasn't changed, but we are viewing the problem in a different way. We're going to try to view the problem with the B as a new independent variable. Now, you may say, well, how would you know that? Where did you get that crap idea? Well, this is the one I was telling you. Now, the next nice story I'm sharing with you is this whole thing was constructed when I was the head of school. Well, we in Australia, we have to, for me, as the head of school, I need to check all the exam papers. So one time, there was one exam paper on my desk. So I was checking, and one of the PDE system, this was a guy who was teaching PDE. And if trying to ask a student to do a question, and I didn't know anything about it, but then suddenly, to me, it didn't make any sense. So I called the staff member into my office and then say, well, what happened? Can you explain this to me? Well, staff member was very nervous, and then turned out that it was she. I can say that. I don't want to give you a name. She was very nervous and then didn't know either. Just got it from somewhere. Okay. So then turned out I then studied, I helped her. It was wrong. She got the problem wrong. So it was an exam question. The problem typed it was wrong. But then I got an idea for this American option problem. This is how the teaching can actually feed into the research. All right, that's enough. So I'll say that. So now the idea is that we're going to view this one B as an independent variable. And then the tau as an inverse function of B. Listen carefully, this is inverse function of B. Then in doing so, then we can change that equation 15, which was earlier, I'm not flipping it back, to this dBd tau. Okay. Once you got that idea, you change your angle of viewing things differently, then you got yourself into a same equation, except now one of the boundary condition is automatically satisfied. You don't need it. And you get yourself into this equation, right? Into this one. From the first sight, it looks, well, it's still nonlinear because you have theta, have the product here. The equation becomes nonlinear. It is nonlinear, right? Now but once we take B as independent variable, you notice that the moving boundary is gone. There's no moving boundary. This B is already become a fixed boundary problem. So somehow the nonlinearity has been shifted from the boundary to the equation itself, which is fine. This is another fundamental principle that I usually tell my students. You cannot expect the inherent feature of a problem to go away. If you have you're dealing with a nonlinear problem, it's very unlikely that you're going to change it to a completely linear problem. That's unlikely. You may at some stage, you may be to avoid nonlinearity temporarily, but eventually, if you can do that, That's already a beautiful way of solving nonlinear problem, which is here it gives you an example. All right. So now watch here. So what I'm going to do is that you'll see in a minute that this term is actually, if you do something, it's not truly nonlinear from another angle. Watch what I'm going to do. The rest I don't have much to say. It's a bit trivial stuff. Okay. So here is the main result. We put it into a theorem. This is basically I'll show you how we get this. Again, I'm not, rather than going through every little detail, I'll just go through the rough idea. But then the theorem is such that we can write this theta in terms of this integral through the Fourier transform. Okay. Now, in a minute, I'm going to tell you why this Fourier transform is going to was successful. It's partially because we treat that equation, the earlier equation I showed you, as a pseudo nonlinear. It's not really nonlinear anymore once you do the Fourier transform, right? The minute you'll see that's where exactly the part I like. I was so thrilled with this part. This MB is just a new symbol. This is just inverse function of that tau. So in other words, apart from a constant, MB for every B, what you calculated is the tau. So in other words, we are calculating the inverse function of the free boundary. Once we got it, then we recover the free boundary through one integral, this MB, equation 19. So basically, we separated the nonlinear problems into two. One is to solve a nonlinear integral equation formulated through the Fourier transform. Okay, now I'm going to show you how we did it. So although equation 17 is still nonlinear, one can establish integration by performing Fourier transform. Now, for those of you who have learned Fourier transform in your undergraduate study, I'm sure that your teacher have told you, well, that can only be used for linear problems. What happened? What happened magically? How could you use it here? This is mainly because, watch here, I'm going back to that 17. This is the one I want to spend a bit more time on. This d theta dx, the partial derivative, after you substitute x on free boundary into it, after you take the derivative and substitute the b into it, it becomes a function of b only, no more x. The Fourier transform is performed against x. This term, as far as x is concerned, there's no more x. So as far as x is concerned, this one is only an inhomogeneous term. Right? So in other words, when you perform Fourier transform against x, equation is linear. That's why it was successful. That's the fundamental reason. But is the equation linear? No, absolutely not. This is a nonlinear source term there. Okay, except when we perform the Fourier transform, it could be treated linear because of that reason. Okay, that's one thing. I think I've made myself clear. 5 minutes, Patrick. I'm watching my watch, so it's okay. It's under control. So that second comment is about what I just said. It's about that this is a function of b, and we already now view b as an independent variable. Okay. Next bit. Right, so this is what I wrote down as a Fourier transform. So no need to say much. Another thing you'll see, this is a proof of that, whatever the theorem before. You'll see that the main reason that we eventually got through is because that delta function. Remember, another thing you learn on undergraduate is that when you perform Fourier transform from the PDE point of view, everybody can do that as long as you have a linear equation, but then you'll have a hard time to find the inverse. Well, here, the beauty for that delta function comes in, and that contributes to the inverse function. So at the end of the day, if we do that, we got ourselves, see this f delta function there, we check, and then you get beautifully this, skip a couple of steps. Then U1 and U2, you can invert it. back to this nice integral equation of MB, which is right here. Sorry, I've skipped a couple of slides with the details. So this is the integral equation that you need to solve for this MB. Let me point it out earlier because I did mention that for this one, you see that there's no derivative of the unknown function MB. Remember, I want to achieve two objectives. One is no derivatives in the integral equation, so that's one. Secondly, no singularities. Well, here, one time, I forgot where I gave a seminar, somebody asked me, hey, what about the when y, because your integration is performed from 0 to b, when y gets close to b, you have a singularity in the denominator. Well, same thing. If you study carefully, you have a similar singularity at the top, in the numerator. So it's a 0 divided by 0. You can prove that it's still, it's called the removable singularity from the PD point of view. So those two, you can remove them. So at the end of the day, in terms of numerical calculation, they seem to be non-existent. So in that way, so you can pretend it that they don't exist. Okay, so that's for that equation. Then where's the discontinuity? That singularity will eventually, when you integrate, trying to solve MB and find the tau at that end point, tau equals to 0 or lowercase equal to capital T. That singularity is still there. You cannot get rid of it. Right? So whatever you had before, at least the advantage of this is that when you solve the integral equation, that integral equation, you don't have to worry about it. It's the afterwards, when you integrate that free surface, your singularity is still there. So I just want to mention that. So that's this slide pointed out. This is the proof that the singularity at the tau equal to 0. So for this formulation, it's not there anymore. Otherwise, when you use other numerical approaches, like finite difference or so, that singularity is always there. It's a part of your numerical solution process that you need to deal with. Okay, so we're nearly there. Let me see. This is after you calculate find MB, how you find the tau. And so that's just inverse function. And then after that, you substitute it back, you'll get the option price through this simple integral. Okay, let me also show you an example in which we did a bit of calculation in terms of numerical values. So what you have here, the blue line is the solution from this integral equation, and the circles are the ones that obtained from my 2006 paper. There are many other papers you can compare with. This is probably handy for us just to give an illustration that works very well, right? So another thing is we also in the paper, we have compared with the speed with other numerical approaches, other integral equations. This one is by far much faster. Right? For that reason, I explained numerically, you are singularity free. Number one, number two, you are instead of integrate by two-dimension integrals, you only need one. So this one has a feature that is much faster, and in that sense, then for today's, if you're trying to, because I was reading about the machine learning and combined with option pricing, this seems to be a new trend. I was reading a paper the other day, and then it looks like you still need to have your underlying program to be fast before you can do all this machine learning. So this one, at least if we write into a code into a subroutine, then this is much faster than other numerical schemes. So let me conclude with the following remarks. First, what I've presented today to you, is a new integral equation to solve American put options. And then another distinguished feature is that unlike all previously derived integral equations for pricing American options, there are three distinguishable advantages of ours. One is in the form of one-dimensional integral, as I mentioned before. It is two. So that three probably should be a two. I'm sorry. Two is a in a form of free form, free from any discontinuity and the singularity. So then this rather unique features, those two, have led to a significant enhancement of computational accuracy and the efficiency, because you can do it much faster, and also because you involve less calculations in terms of the convolution of integrals. So it's for the same accuracy of requirement, this would perform much better. Okay, Patrick, that's all I have. Exactly your 450.
Thank you very much. Thank you very much for the interesting talk. So I learned a lot from the talk. And let me check with the audience or the participants. Any questions or comments for Professor Zhu? Yeah, I think when perhaps when the audience are thinking about the questions, perhaps I check with Songping one very simple question, maybe a naive question regarding the new integral equation. Should we be concerned about its solvability, or is guaranteed by the solvability of the PDE? Or?
That's a beautiful question. I was about to comment, Patrick, that you said it's simple and naive. Nothing is simple and naive from a very young, dynamic guy like yourself. Well, if you proved that the question you asked is not really simple and naive. Okay, let me tell you. Usually, this is to answer your question, solved in terms of solvability of integral equation. There are two sides of this question. First, if one thing that people need to be aware of is that usually integral equation can be viewed as another way or another form of PDE.
Yes.
So in some way, the two of them are twin brothers. Although there are certain numerical advantages of casting a problem into integral equations and solving PDE. But that's not always true though. Sometimes the PDE themselves has advantages. One of which is the question you are asking, right? The solvability. Now, the reason for this is quite often for the PDE side is a very rich theory in terms of solvability of the PDEs, and then convergence, uniqueness, and all that on the PDE side. But again, for that, usually those we're referring to non-linear PDEs. Once you step into the non-linear PDEs, boy, those guys, their hands are tied too. There's not much there, right? So this is point one. Number two, the reason why I'm pointing this out is that in terms of solvability, quite often on the PDE community, people less examine the solvability on the integral equation side, because they are assuming that if the solution exists and the uniqueness, everything you can prove on the PDE side, then on the integral equation side, because of that first point I was mentioning, it's just a different form.
Yes.
And they would assume that the solvability is still there.
Yeah.
Okay, so that's in the literature. But you ask a very good question. The reason this is so profound is that let me explain this in a different way. You actually inspire I would have to think it a little bit further, because who said that solvability is guaranteed? Once you, I don't know. You got me. I don't know. I'm gonna have to check. Right. So
yes.
At the end, I sort of try to answer it in one way, but then at the end, the honest answer is I don't know. So it's very good, particularly if it's a nonlinear problem. Then usually, even on the PDE side, there's not much you can do in terms of theoretical proof. Now on the integral equation side, that's even harder, I'm guessing. So on the theoretical proof for that.
Yeah,
I don't know if that I have answered your question, but then
definitely.
You can see it's not simple, nor is it trivial at all.
Yeah, there is also what I speculate about the solvability of this integral equation, because it comes from the PDE, and the parabolic PDE over there do have the well-postness results, and no wonder people will just continue with the integral equation and perform all kind of calculation. But by looking at the integral equation there, I'm thinking about whether we can apply the fixed point theorem to prove the fixed point of the solution, and that sounds doable, and that is what I thought. But I believe that may take a longer time to really investigate, and that is actually I would say I didn't have much experience about that. That's why I would like to call it a naive question, but yeah, that is.
I wouldn't say that's naive. That's actually my sense is, let's say if we use a fixed point theorem or a fixed point theory to do some proof like that, my feeling is that would be a mathematical finance paper.
Yes.
So you see, that's not really naive, because that would be really something quite deep in my view.
Yeah, it's true. Okay, so let me check with the audience again. Any questions or comments for Professor Zhu? Okay, maybe one last question I would like to ask is that this approach is very beautiful, that we can use it to get rid of the singularities. I think that may be the main point. And the second one is to get rid of the derivatives in the integral equation. But other than the American put options, do you find any other products or any payoff structure will also allow us to do so? So what will be the key in American put option that allow us to use the integral equation approach here?
Again, that's a good question too. First, to answer for the payoff, if it's not this payoff, a bit more general payoff, would that affect the application of this? Let me try to think. It could. I don't know. The only thing is there's some steps you may still go through, in the sense of what I said earlier, right? The in terms of performing Fourier transform, you may still be able to do that, but for different payoff, the inversion may not be there. That you may destroy that delta function, so that may not be there. So I'm not 100% sure. I need to think about it again, Patrick. This is not naive at all. So that so you are talking about mainly the versatility of this approach. How versatile? How can, whether or not you can you can extend this to other cases. Payoff may not, but then at the moment we're trying to do for other types of models that may be possible, right? So there are certain advantages for other type of models, not necessarily the payoff. In terms of the payoff, I'm not sure. I need to think about a payoff if you ask that. Other models, that's possible.
Yes. So I noticed that one key step is to apply a transformation on B tau. I forgot the arguments, but B function B, and replace the T or S. I forgot the time variable.
You want me to go back?
With B. Yeah. When I saw that, I actually I had a quick question that whether we actually require the theta to be regular enough for us to, apply this transformation, because later on you're going to do the inverse transform from B. So somehow the theta.
What did you say? The feature? One word I didn't get it. What did you say earlier?
I mean the theta. The theta should have enough regularity about the second argument in order for you to do the inverse transform.
Yeah, sorry, I still didn't get it. The theta, did you say theta?
Theta, yeah, the theta function.
Oh, theta, okay, theta function. Oh, I get it. Yeah. So you're talking about this.
Yeah,
theta.
correct.
Yeah.
So So we need certain regularity in X or in B in order to perform the. In order to maybe apply this approach, that is my. I don't know.
That's a good point. Okay. Let me tell
because applying the B inside the second argument. So
I understand.
we need certain regularity. I believe.
I understand. I understand what you're saying now. I didn't get that one word. Okay, let me comment this again.
No, I think that is just
beautiful question. Beautiful question. Some of the stuff I've never thought about before. Let me comment in a slightly different way. You are asking about this inversion of B, right? That really, that's not a problem, because all you need after you find this MB.
Yes.
And the recover of tau is through this equation. That's just one single integral. Right? So this through this equation, 19. So that you can know. So you were talking very because the theta is involved here. My sense of feeling is that theta is actually what we have done is to raise the order of the PDE one order up. It requires certain smoothness of the original function P in the functional space, right? So so to answer you, that's good. So in other words, maybe I didn't say it in the paper, you raise a good question in terms of theta. Yes, there is a certain, we have to make an assumption that the original function is smoother than what other people would use the PDE to solve. In that sense, then it's okay. That's a good point. So that's roughly to answer your question, this one. Yes. In terms of recovering it, it's okay, but then we need higher smoothness of the original option function.
Yes.
So that's part of the mathematical assumption. If we have that, it'll be all right. Yes. Okay.
Okay. Thank you very much. I think
Patrick.
we are we're running out of time. So I will be more than happy to talk to you more when you visit us. And I look forward to it. So any audience who would like to have any collaboration intention with Prof. Zhu can contact me. Okay, so I'm going to call the end of this session. Let's thank our speaker, Professor Zhu, again. Thank you very much.
Thank you.
Thank you, Professor Zhu. Okay.
Thank you very much.
Have a nice day.
I look forward to meeting you too. We'll talk about some other modern problems.
Sure. Thank you.
Have a good afternoon there in Singapore.
Thank you. Bye-bye.